Good afternoon, everyone. We are Team TF, and our project sought to develop a clamp for a neonatal feeding tube. Currently, nurses in low-resource settings have to feed tiny babies with milk from a syringe into a nasogastric tube, which takes up valuable time and effort and can be subject to human error. Just using gravity, the feed goes way too quickly for the babies, feeding at a rate of 2 ounces in approximately 2 minutes, whereas the acceptable rate is 2 ounces every 15 to 30 minutes. Ideally, NG feeding pumps would be used to adjust the feeding rate digitally, but this is not a feasible option in low-resource settings with limited access to high-caliber medical equipment. To tackle this issue, our team set to design a mechanism that can safely, cheaply, and efficiently regulate the rate at which milk is delivered to neonates. To accomplish our goal, our team first looked at existing and effective technologies. The IV roller clamp is the current standardized device used to control the flow rate of IV-administered fluids to patients in hospitals. Its ability to control flow rate with no motor force input makes it an attractive potential solution to our problem, and we decided to reimagine and optimize the roller clamp design to best fit the needs of our project. Specifically, and keeping in mind that our device is targeted towards low-resource communities, we sought to emphasize 4 critical pillars in our design: accessibility and low cost, ease of use, high accuracy and sensitivity in the clamp readings, and high durability of our device. These pillars were essential in our design process and allowed us to prioritize accessibility and affordability while maintaining high accuracy. In order to achieve these goals, we first began to understand the need for our device by conducting research and meeting with experts in the fields involved. Guided by this information, we were able to develop design criteria and begin brainstorming potential solutions. After initial prototyping, we decided to take our final design and begin developing the device further with CAD and 3D printing. We conducted testing to obtain data and see the magnitude of clamping that is necessary to produce the desired flow rates. Informed by these results, we were able to finalize our CAD model and begin 3D printing a working prototype. Because our design is meant to be used in low-resource settings, our priority was first to minimize the cost of our device. Scaling down the dimensions of our device would serve to both reduce the cost and make the device suitable to use in smaller-sized nasogastric tubes on neonates. We also aim to increase the durability of our device by using heat-resistant material in order to allow the device to be sterilized, which would allow the device to be safely reused in cases where buying new ones is not an option. Finally, in order to optimize the user interface, we designed grooves along the roller axis to lock the clamp into place at 5 different settings. This allows for consistent accuracy and precision in setting the clampage. This is necessary and critical because of the high sensitivity of the clampage system. We quantified our goals into the following design criteria: cost, time of feed, durability, ease of use, and size, each with specific target values listed. We gave them weights or percentage-based priority values in order to guide our design selection process and come up with a plan for testing each criterion.
To visualize our concept, we made a low-fidelity prototype with a wheel and an axle and tested the functionality by running a tube through it and clamping on the tube as seen in the picture on the right. But before we could finalize our design, we had to test for the desired tightnesses of our clamp, which would correspond to the different rates of feeding. To do so, we used an 8 French catheter as a pseudo-feeding tube and clamped the end with a digital caliper so we could both measure the clamp that we administered as well as precisely repeat the conditions. We then ran half an ounce of milk through the tube from an open air syringe and measured the time that it took for the milk to flow through. To gauge the time that it would take for an actual feeding amount of about 2 ounces, we simply multiplied the measured time by 4. We also ran a few tests with a solution of formula to account for different feeding. Our test results can be seen on this slide. We determined a 0.85 millimeter clamp as a maximum setting because tighter clamps didn't allow for milk to flow through, and it also matched the desired 30-minute flow time for 2 ounces of milk. We also decided that a 0.89 millimeter clamp should be the minimum to allow for possibility of slightly faster feeding time as well as lower volumes of feed. Thus, we were able to determine the 5 different levels of clamping from 0.85 to 0.89 millimeters, changing by increments of 0.01, which we implemented in our CAD model design.
Based on the testing data, we determined the final measurements needed for our design and created a 3D model in SolidWorks. The diameter of the titration is equal to the distance between the roller wheel and the plastic body. So in our case, the distance ranged from 0.85 millimeters at the smallest to 0.89 millimeters at the largest. Using the CAD model, we 3D printed a 2 times scaled up version to use as a proof of concept. The roller wheel, seen in black, can move freely along the long axis of the clamp in orange and uses friction to titrate a tube. We conducted some preliminary tests. The first was the manufacturing cost test. We used 3D printing costs as opposed to plastic molding due to its availability in low resource settings. Also, we chose ABS plastic due to its ability to be sterilized, leading to a cheap initial cost and reusability, which will save money in the long term. Based on current market prices for ABS plastic at around 5 cents per gram and the weight of our device around 3 grams, we estimate the total cost to be about 15 cents per unit. Compared to commercially available large roller clamps at 2 cents per unit, this seems expensive, but when compared to electric pumps, which cost hundreds of dollars, it's much cheaper. In order to prepare our device for use, we will first need to create a CAD model that incorporates notches for the different widths necessary determined by testing. Once this model has been designed and printed, we will need to conduct further testing to confirm the necessary flow rates are consistent with the needs of the user. Then, we will be able to plan for the manufacturing of the device in a low-resource setting, including finding available 3D printing facilities. Once this has been completed, we will just need to create instructions for use, sanitization, and manufacturing that will allow for our design to be implemented. We really appreciate the opportunity to work on such a fun and impactful project, and if you have any questions, please direct them to our team.